Hello online viewers, welcome to our lecture video. In this lecture video, we'll be solving our problem 4 of chapter stress and strain, and here our question reads as: find the total extension of the following steel bar. Take Young's modulus velocity E equals to 2.05 into the power 5 Newton per m square. As you can see here, a steel bar which consists of 1, 2, 3, 4, 5, 6, 7, 8 sections, and each section has its respective length, and they have its respective diameter of 120 mm, 80 mm, 100 mm, 100 mm to up to 120 mm, and there are two forces of 800 kilonewton acting at left and right at the end of the bar. The question seems a bit tricky at first, but the question is not as tricky as it seems. So firstly, what we need to do is we need to check the condition for equilibrium. Condition for equilibrium. So so we have so So in order to check whether this steel bar is in equilibrium or not, we need to have the sum of original forces to zero. So we have 800 kilonewton acting at left. So I'm taking it as positive, and 800 kilonewton is acting at right. So I'm taking it as negative. This is equal to 0. 0 equals to 0. So this steel bar is in equilibrium. So the individual sections, this is an average sections are also must be in equilibrium. So let me first take this section. So I'm taking this first section. So what is happening over here is a force of 800 kilonewton is acting at the left. So in order to maintain equilibrium, a force of 800 kilonewton must act at the right. But as you can see, no such force exist over here. So what we do? So let me just take these two sections at first. This two section. This is my first section. This is my second section. So as you can see here, 800 kilonewton is acting at left. In order to maintain equilibrium, a force of 800 kilonewton must act at right. So 800 kilonewton must act at right. This is 800 kilonewton. But as you can clearly see, no such forces exist over here. So what we simply do is we suppose another force of 800 kilonewton of same magnitude but acting in opposite direction. So in this way we can suppose any forces. So any forces. So in this way our first block is in equilibrium. Now what we do is we take our second block. So what is happening in our second block is 800 kilonewton. We have two components of 800 kilonewton. One is acting at the right and another is acting at left. The one which is acting at right has already been written over here. So the another one which is acting at left, we write it over here. So in order to maintain equilibrium, another force of 800 kilonewton must act at right. So now what we do is we take these two sections. So let me draw these two sections over here, smaller section and the bigger section. This is my second and third section. So what we can see over here is 800 kilonewton is acting at left, and in order to maintain equilibrium, a force of another 800 kilonewton must act at right. But again the same case as first, no such forces exist. So in order to maintain no such forces exist over here, exist in the boundary over here of 100 mm and 200 mm, this second and third block. This is my second, this is my third, this is my first block, this is my second block, this is my third block. No such forces exist over here. So what I simply do is I suppose another equal and opposite force. So under that condition only I can suppose another force of 800 kilonewton. So now my block 1 is equilibrium, now my block 2 is equilibrium. Now let me take block 3. So what is happening over here in block 3 is the 800 kilonewton which was acting at right has already been taken over here. So the remaining 800 kilonewton which is acting at left, I'll simply write it over here. So in order to maintain equilibrium, another 800 kilonewton must act at right. So as you can see here, we are following a particular pattern. 800 kilonewton is acting at left, 800 kilonewton is acting at right. The same pattern will be followed till end of the box. Till end of the box. So we have a common force P equals to 800 kilonewton. 800 kilonewton. So as you can simply say from this, in each and every section 800 kilonewton is acting at left and right in order to maintain equilibrium. So our only force acting in all this steel bar, in overall steel bar, is 800 kilonewton. So in order to find our total extension del, what we simply will be doing is del 1 plus del 2 plus del 3 plus dot del 1 2 3 4 5 6 7 8 plus del 8. So what we have, what we have for del 1 is P1 L1 by AE by A1 E plus P2 L2 divided by A to E. They have same Young's modulus of elasticity 2.05 to the power 5 Newton per mm square, but they have different they have different area, as they have bearing diameter plus dot 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 P8 L8 divided by A8 E. So as you can see here, we have a common force P equals to 800 kilonewton. So I can take P as common and P as common and P as common. I can take E as well as common, and what I have and what we have for area is pi by 4 into d square. I can take pi by 4 as well common. So what is remaining is L1 by d square d1 square plus L2 by d2 square plus dot 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 L3 plus L8 divided by d8 square. So let me write P, which is common over all here, 800 into 10 to the power 3 into 4. I have taken this P of numerator. Pi into E is 2.05 into 10 to the power 5. And we have L1 is 200 mm divided by D1 is 120 square plus L2 is 100 divided by 80 square plus L3 is 250 divided by 100 square plus 150 divided by 80 square plus 250 divided by 100 square plus 150 divided by 80 square plus 100 divided by 100 so this is 200 divided by 100 square plus 200 divided by 120 square. Simply L1 divided by d square. Now on solving this, I will simply get my value to be 0.796 mm. So it will be easier if we if we calculate individual deformation, it will be a bit difficult. So if you so the easier trick for this question is you need to calculate the deformation at once. So you can take a P, pi by 4 and E as common, and the process will be much simpler and shorter. So in this way we can simply solve this question. So if you have any queries, you can comment down below, and if you like our content and if you want to see more of such video, do subscribe the channel. Thank you.